right, so hello everyone. Today we're very pleased to have Tat-How Teh from the Nanyang Technological University, who's going to talk to us about network interoperability and platform competition. The presentation will last for 40 minutes, and then David Ronayne will discuss the paper. Tat-How, the floor is yours.
All right, thank you, Alex. So hi, everyone. Today I would like to present this paper, Network Interoperability and Platform Competition, which is a joint work with Jing Lei and Junji from Tsinghua University and Guo Fu from USC. So any comments, feedbacks are more than welcome. So let me get started. So the starting point of this paper is our platform market, by which we mean firms selling products with network effects. So the more users there are, the more valuable the product becomes. So in this space, there has been a lot of regulatory discussion going on. So one issue that has received a lot of attention is network interoperability. So by that, we refer to general phenomenon where users who are single homing on the platform do not just exert network benefits on other fellow users on the same platform, but they also exert network benefits to users on other platforms, but potentially weaker. So similar terminology has been used, such as horizontal interoperability and interconnectivity, to refer to similar general phenomena. So how does network interoperability arise? So it can arise due to a few reasons. One is regulatory mandates, which regulatory mandates such as those in the telecommunication industries. So users on different telecommunication networks can communicate with one another. It can also arise due to data sharing. So that relates to the notion of data-driven network effect. So that reflects the idea that when there are more users on platform one, that generates data, which platform one can use to improve its products. And that benefits other users on the same platform. So if there's data sharing, then data generated by these users will be used by platform two to improve its product, which benefits users on these platforms. So there is interoperability in that sense. Finally, it can also arise due to standardization and the existence of complementers. So to fix ideas, let's think about some classic examples such as these player devices. So those are the platforms here. So when there are more users for a specific device of a manufacturer, let's say it is using the Blu-ray format, that attracts more content to be produced under the Blu-ray format. So that benefits users of this particular device, but also other users of the device under the same file format due to this increased content for Blu-ray devices. So that's the broader idea that could be applicable to smartphone devices. Those are the platforms here in the standardized Android ecosystem. So our purpose today is to look at the implications of network interoperability. So in terms of the price, competition outcome, consumer surplus, and the dominance of leading platforms. So we will do that in the context of price competition model of Armstrong 2006. So when I bring out examples such as Blu-ray and HD DVD, then you can see that this is a fairly classic question. So what are the new twists we can offer today? So we propose a framework that investigates the notion of interoperability via two dimensions. The first is interoperability strength. So to how much network benefits is platform sharing with other platforms. Second, interoperability configuration, to whom the platform is sharing network benefits with. So for example, you could have an industry-wide configuration where everyone is sharing network benefit with everyone. Or you could have a correlation-based configuration where the platform only share the network benefits within the same correlation, but not across correlation. So let me just briefly give you an overview of what I'm going to do here. First, I will characterize the equilibrium for general interoperability configurations and provide some interpretation. Second, I will do comparative statics exercise. So fixing configuration, what are the implications of increasing interoperability strength lambda? And fixing lambda, what are the implications when we compare configurations? So such as adding links or allocate link strengths around. So let me jump straight to the model and then I will pause for questions. So there's a set n of symmetric one-sided platforms. So we are going to reflect these symmetric assumptions later. There's a continuum of heterogeneous consumers. Each consumer is described by a vector of idiosyncratic match values, epsilon1 until epsilon n. And those are describing consumers' horizontal preference for the platforms. So those are drawn from some smooth joint CDF, which is described by F function here. Each platform I competes by setting membership price PI, which consumer has to pay to join the platform. We denote the participation mass on platform I as Xi between 0 and 1. We assume single homing and full coverage, meaning that each consumer joins exactly one platform. So if a consumer participates on platform I, the utility is given by the following expression. The idiosyncratic match value minus the participation or membership price plus the network benefits. In a world where there's no interoperability, that network benefits is just going to depend on the participation mass on the same platform, so Xi. Gamma here is a constant, which reflects the network benefit parameter. If there's interoperability, what goes in here is now Zi, which is the effective network size accessible on platform I. So naturally, that should depend on the participation mass on the same platform Xi, as well as a weighted sum of participation mass on all other platforms, J. So the weight here, lambda, is what we call the strength of the interoperability between platform I and J, and it is between 0 and 1. So you can see that this lambda ij is going to be the key object. So let me describe that a little bit more formally. We assume that there's an exogenous interoperability matrix denoted as capital lambda. Each of its entry indicates the interoperability strength between platform I and platform J. And by convention, we assume that the diagonal entries of this matrix is 0. So the idea is each matrix corresponds to a graph like this, and each node is a platform. And the link indicates whether there's interoperability arrangement between the two platforms or not. So industry-wide and correlation are the examples. We make two assumptions. First, this matrix is symmetric, meaning that the network benefit sharing from I to J is the same as from J to I. Second, we are going to solve for the symmetric equilibrium in the baseline model. So we need some notion of symmetry across platform in terms of this network position. So the formal assumption for that is called vertex transitivity. The idea is essentially each platform or node are the same in terms of their location on this graph. So you can see that 1 and 2, they are basically the same. Each of them is connected with 5 other platforms. Likewise, over here, 1 and 2 are essentially the same. Okay, they are linked with 2 other platforms and they are in different correlation. So the direct implication of this vertex transitivity is every platform I is going to have the same number of links in a weighted set. So specifically, if we take some platform I and we sum its strength across all other platform J, we are going to get a constant that is the same across all the platforms. So the timing of this model is fairly standard. So platform set prices to maximize the profits. So we normalize the marginal cost to be 0, and then consumers participate. Okay. Any questions so far in terms of the model setup?
Yes, please. Can you explain a little bit more why we should accept the vertex transitivity assumption? It was very strong, and I
Yeah, so
don't
this is just
understand the economics of it.
right. So I would say this is quite of a technical assumptions to gain tractability. So we are going to try to look for symmetric equilibrium. And so this is essentially saying that we are assuming platforms are symmetric so that we can get symmetric equilibrium. But we notice that this is definitely wrong. So towards the end, we have this extension with asymmetric platform where we look at things like star network, which is not vertex transitive, for example. But at this point, I can just say that this is just made to ensure that we get symmetric equilibrium. All right, thank you. Okay, let me just move on. Okay, so for the sake of time, I will just jump straight to the pricing equilibrium. So to describe the equilibrium, let me define the adjusted never benefit coefficient as delta, which consists of this H. This is a inverse measure of the extent of product differentiation across the platforms. So formally, it is the density function of this idiosyncratic max value difference across the platform. So this is twice continuously differentiable, and we assume it is log concave. So this is a standard discrete choice object. So for example, if you think about a hot-tiling model, then this is just 1 over transportation cost. Okay, so inverse product differentiation. This is never benefit, and then adjusted by the number of platforms. So roughly speaking, this is capturing how strong the never benefit is compared to the extent of product differentiation. So for example, if there's no never benefit, no never effect, this is 0. Okay. Now, naturally, to ensure that we get a symmetric equilibrium with the coexistence of the platform, we assume that this delta is not too large. So with that, we can get the following equilibrium characterization. In any symmetric pricing equilibrium, all platforms have the same market share 1 over n, effective network size, which is just adjusted by the interoperability strength, and then set the price that is given by the expression here. So I want to emphasize that this is a closed form solution in the following sense, because the right-hand side only consists of the model primitive. So the number of platforms n, the extent of product differentiation, and all this little a, which are just the entries from what we call the amplification matrix. So the matrix is just coming from identity matrix, interoperability matrix, and this adjusted never benefit coefficient. All right, so let me try to unpack this a little bit more by offering 2 interpretations. So the first is a more technical network-based interpretation. The idea is we can write the equilibrium price as 2 separate terms. A standard oligopolistic markup adjusted by this additional term. In a world where there's no never benefits, this will equal to 1. So we are just left with the oligopolistic markup. So this term captures how never benefits and never interoperability modifies this standard markup term. So the key terms are all these little a, they are just coming from this amplification matrix. Following the standard approach in social network analysis, we can unpack this as an infinite summation form. All right. So with this infinite summation forms, it has a very convenient interpretation. Each of its entry, AI1, for example, indicates the discounted sum of paths originated from platform I and ending at platform 1 on the graph of identity plus the interoperability matrix. Okay, so just looking at the graph and then count the sum of paths. So you might ask, why does this matter? Why do we have discounted sum of paths here? So the idea is it is going to describe 2 distinct chains of effect when platform 1 cuts its price P1, okay, and which is why they appear here. So the idea is if platform 1 cuts its price, the first effect of that is we will get more participation on platform 1, okay, and that leads to larger effective network size on platform 1, and that leads to more network benefits, and that allows platform 1 to attract even more participation on platform 1. So you can see that this chain of effect makes it attractive to cut the price because that amplifies the demand gate. So which is why the larger this sum of path is, A11 from 1 to 1, the lower the price is, okay? Because it becomes attractive to cut the price. At the same time, there's an opposite effect when platform 1 cuts its price, because when it cuts the price, it is going to attract consumers away from the partner platforms. So that leads to less participation on the partner interoperable platform. That leads to smaller effective network size on platform 1 due to interoperability, and that reduces the network benefit offer to lead to less participation on platform 1. So you can see that in contrast to the previous chain of effect, it has the opposite effect of less participation. So this indicates that it becomes less attractive to cut the price. Okay, because by cutting the price, I have this negative downside on my participation. So we can see that as the sum of half here increases, the price increases. Okay, so it goes in opposite direction. So the idea is the network-based interpretation here highlight two opposing chain of effects in the demand system where we cut the price. The second interpretation, which is more intuitive, IO style interpretation, is to rewrite the pricing expression as the following form. So we have this additional term that reflects the role of network interoperability. For example, if there's no interoperability, lambda equals to 0, so this entire term becomes 0. So what is this term? The blue term here is the standard Carson-Shapiro demand diversion ratio. So over the numerator here, this is your cross price derivative, and this is the own price derivative. So the idea is if platform one raises its price, how much of its users will be diverted to its partner platform J. So that's what demand diversion ratio tells us. And intuitively, we get demand diversion ratio here because interoperability means a platform is going to internalize how its pricing affect the demand for its partner platforms, right? So which is why we get demand diversion ratio. So in standard setting, we know that this demand diversion ratio is going to be positive because products are substitutes. So you have a positive term. And so if you compare this to a world where there's no interoperability, where this is 0, then this expression is suggesting that interoperability leads to higher price because platforms are going to internalize substitution to partner platforms. So they are more incentivized to raise their price. But is that always the case? It turns out that it is not. Okay. It turns out that interoperability also affects the nature of this diversion ratio and sometimes flip the sign to be negative. So let me describe that a little bit more by charging into the first application, which is how does a higher interoperability strength affect price and consumer surplus? So it turns out that the answer depends on the exact configuration we are looking at. So if we zoom into industry-wide, you get price always increases. But if you look at the correlation setting, you get the opposite outcome. So let's zoom into those two configurations. In the industry-wide setting, everyone is sharing network benefit with each other with strength lambda. In that case, proposition 1 specialized to a very simple closed-form solution. For correlation configuration, we partition all platforms into mutually exclusive correlation, and each correlation has n member platforms. Within each correlation, there's a sharing of network benefit of strength lambda. And then there's no sharing across the correlation. So you may think of this as like your Blu-ray HD DVD or your VHS Betamax type of correlation, for example. We restrict the number of correlation, which is n over m, to be integer, and restrict it between 1 to n. So for example, if the number of correlation equals to 1, then there's just a single correlation. So that's equivalent to industry-wide. So we rule that out. Likewise, if the number of correlation is n, then it means that each platform is itself a correlation. So that's basically 0 interoperability. So we rule that out as well. So in this configuration, we get an equilibrium price, which is a bit more complicated, but still a closed-form solution. For both configurations, consumer surplus is equilibrium is just the expected idiosyncratic match plus the network benefit minus the equilibrium price. So we are going to do next is to take derivative with respect to lambda for all these objects. And we get the following result. In the industry-wide configuration, price always increases in lambda for any lambda. In the correlation configuration, price initially increases in the strength of interoperability, and then it decreases. Meanwhile, for both configurations, consumer surplus always increases in the interoperability strength. So the key here I want to emphasize is the distinct price pattern between this industry-wide configuration and correlation configuration. The one is always increasing, one has the inverted U-shaped pattern. So what explains this contrasting price pattern? So for that, we can return to the pricing expression to get some intuition. So we call this the pricing expression, and we have diversion ratio here. In the industry-wide configuration, the demand for platforms exhibit substitutability, so positive diversion. So this is positive term. So when lambda here increases, each platform is going to internalize substitution to the partner platforms. So meaning that they are more willing to raise their price. So intuitively, as you increase lambda here, so price increases. Okay, so there's the existing intuition that you can see from Doganoglu and Wright and the recent paper by Agnetti et al. But for correlation configuration, this diversion ratio becomes negative. So platform exhibit complementarity. So in this case, we get a reverse pattern where a higher lambda now causes platforms to internalize complementarity with the partner platforms. And so they become more willing to cut price instead. Okay, so negative term here, increase lambda, price decreases. Then the question is, what gives rise to this complementarity? So to explain how that complementarity arises, let me focus on the situation with 4 platforms and 2 correlation. And suppose initially platform 1 decreases price. So the first effect of that is it is going to attract consumers away from all other platforms to platform 1. So in particular, there's an outflow of consumers from the partner platform 2 to platform 1. So initially, a decreased outflow effect. At the same time, because of this increase in the participation mass on platform 1 and interoperability, platform 2 is going to offer more network benefits due to interoperability compared to the rival correlation. And so that increased network benefit allows platform 2 to attract consumers away from the rival correlation to itself. So there's an inflow to platform 2. So when the interoperability is strong enough, that inflow is going to dominate the outflow. And so that results in a negative relationship between the price cut on platform 1 and this participation mass on platform 2. And so that results in within correlation complementarity. So to summarize the main takeaway here, let me illustrate this with the following graph. So here, the x-axis is the interoperability strength, and y-axis here is the equilibrium price and the consumer surplus here. So for the price result, if we focus on an industry-wide configuration, then it always increases in the interoperability strength, reflecting the existing intuition on platform internalizing substitution to the partner platforms. But in the correlation setting, then we have the opposite price pattern because now instead of internalizing substitution, they internalize complementarity. Okay, so the price decreases. Meanwhile, for consumer surplus, they always increases with the interoperability strength because the expansion in network benefits always dominates the potential increase in the price effect. Okay, so now the question is about this one, internalized complementarity is what we think is a relatively novel finding. Then the question is, to what extent this is robust, or is it very specific, very nice edge to correlation setting? So for that, we can return to our previous illustration. Okay, so for the previous complementarity logic to work, the key ingredient here is the price cut by platform 1 raise the network benefits offered by platform 2, making it more attractive relative to some outsiders. So what's important here is some sort of insider-outsider distinction from platform 1 and platform 2's perspective. So in our correlation setting, this outsider is the rival correlation. But I can see that this can be replaced by other things, for example, such as outside option. All right. So in fact, in this 2019 JP paper by Ray and Tyrrell, they have a very nice hoteling example where firms act as interoperable platforms and act as local monopolies, and their demand complementarity arises. And in our extension, we also look at partial market coverage where there's an outside option, and a similar idea of this complementarity continues to hold as well. So what we want to highlight here is that this logic of complementarity between interoperable partners is quite robust and not just specific to this correlation setting. Okay, so the next application is we compare configuration in terms of their performance in various dimensions. All right, So this could be relevant if we think about questions such as a privately or platform optimal interoperability configuration versus the consumer surplus optimal configurations. Well, there's a very low-hanging fruit here. So the first low-hanging fruit here is we have done the industry-wide and correlation configuration, so we can just compare them directly. So here's the result. For all lambda, industry-wide configuration always leads to the higher price compared to the correlation setting. Consequently, the consumer surplus in the industry-wide setting can be lower than the correlation setting if the interoperability strength lambda is large enough. So the main insight here is that industry-wide interoperability does not always maximize consumer surplus due to its higher equilibrium price. And so this result more generally highlights the potential gain for the researchers by considering alternative configuration that move beyond the very classic industry-wide interoperability. Now, how about moving beyond these two configurations and compare beyond that? Okay, so this is generally a difficult question because there are many possible configurations to think about. So to operationalize that investigation, we will focus on n equals to 4 platforms. With that, we can parameterize all feasible configuration with a vector lambda 1, lambda 2, and lambda 3. So roughly speaking, lambda 1 corresponds to the strength of these two red links, lambda 2 corresponds to the strength of these two blue links, and lambda 3 corresponds to the strength of these yellow links. So in terms of metrics, it becomes something like this. So for any lambda 1, lambda 2, and lambda 3, they are all vertex transitive, and so they can be analyzed with the existing symmetric equilibrium structure. So this nests a few specific configurations such as correlation, industry-wide, and their convex combination. So for each given lambda vector, we can denote the equilibrium price as P star. Then with that, we can do many possible configurations such as comparing between adding links, reallocate links, or convex combination. So there are many possibilities. Now, instead of exhausting all possibility, we thought it is probably easier and more effective if we just look for configuration that leads to the lowest or highest prices and consumer surplus. So towards that direction, as an intermediate step, suppose we consider the following sub-question. Okay, we reallocate link strength across lambda 1, lambda 2, and lambda 3 while fixing the total sum of strength. So you may naively think of this as a planner facing a resource-constrained allocation problem. So that leads to the following technical lemma, which says that for any two configurations with the same total interoperability strength, the one that has the more concentrated allocation of the link strength leads to the lower price. So that concentration of the link strength is formally described as majorization ordering. But I won't go into the details here, but I will just look at examples. Okay, so suppose that the total sum of strength is less than 1, then putting all those strength on a single pair of links, such as correlation configuration, is going to be the most concentrated, so the highest in the majorization ordering, compared to spreading it equally across all pairs of links, such as your industry-wide interoperability. So that corresponds to the lowest ordering in terms of majorization ordering. So this is the highest, most concentrated. This is the least concentrated. So this says that the correlation will give you the lowest equilibrium price compared to industry-wide interoperability, which gives you the highest equilibrium price. So what's the intuition here? Well, a more concentrated allocation, we can think of it as a sharper insider-outsider distinction that I highlighted earlier, which is the key ingredient for the complementarity logic to arise. So more concentrated allocation, sharper insider-outsider, that results in platform internalizing complementarity with the closer partners. And so that gives incentive to cut price. So building upon this result, we show that equilibrium price and platform profits are maximized at the industry-wide interoperability, and consumer surplus is maximized at either the correlation or the industry-wide. So this suggests that in terms of platform profits and consumer surplus, it suffices to focus on industry-wide or correlation configuration. So partially justify our focus on this comparison previously. And more generally, it highlights a divergence between the platform optimal configuration and consumer optimal configuration. Okay, we have a few extensions in this paper, and I want to specifically highlight this asymmetric platform competition. So let me jump straight into that. The policy discussion on interoperability often focus on context with a single dominant platform competing against smaller platforms. So we now relax our symmetric assumption as follows. We look at configuration in a dominant-fringe competition. So there's a leading platform 1 with a standalone product value V1 and N-1 fringe platforms with product values that is lower than this platform 1. So this is going to be an asymmetric competition setup, which is notoriously difficult to solve, even if there's no interoperability or network benefits. So to make things tractable, we make two simplifying assumptions. First, we impose a logic demand form, which allows us to apply this aggregative game technique. Second, we assume that price by the fringe platforms is exogenously fixed at some price, P greater than 0. So as a justification, we can think of this as a limiting case when the number of fringe platforms goes to infinity in the logic continuum model, such as those analyzed by Anderson and Bertrand. And you can indeed get an exogenously fixed equilibrium price in that setting. So with that, we can also drop our vertex transitivity assumption that Jack mentioned just now. So we compare between 3 configurations. So first is a star configuration where all the fringe are connected with the leading platform, but not among themselves. Second, the fringe are connected, sharing network benefit with each other, forming a correlation and fight against this leading platform. And lastly, industry-wide, everyone is connected with everyone. We compare this configuration in terms of their performance over 2 objectives. First objective is mitigate dominance of the leading platform. So specifically, we mean lowering equilibrium market share of platform 1. Second, we look at consumer surplus. So which configuration gives us the highest equilibrium consumer surplus. So ex ante, it is actually not clear which one performs better. So which makes this investigation interesting. And it turns out that the result is going to depend on the relative advantage of platform 1, meaning that how dominant it is relative to the fringe. So we need a parameter which describes this difference in the product standalone value between platform 1 and the fringe. Instead of stating the former proposition, let me just show you the graph here. So x-axis, relative advantage of platform 1, y-axis, market share of platform 1, and consumer surplus. So here we see that when platform 1 is has a sufficiently large advantage, star configuration performs the best in terms of lowering the platform 1's market share compared to industry-wide and fringe correlation. Meanwhile, for consumer surplus, industry-wide always perform the best. So more generally, this suggests a trade-off between 2 objectives when platform 1 has a huge lead. Star configuration gives the lowest equilibrium market share because that corresponds to the configuration that levels the playing field across the platforms. Meanwhile, industry-wide is better in improving consumer surplus because intuitively that leads to the highest network benefit in the market on largest effective network size in the market. And that turns out to dominate any potential price differences. So the insight here can be confirmed with this formal proposition. So we proved, so this proposition basically proves what I have the graph I have shown just now. So when platform 1 has a sufficiently large market share, Star network performs the best in terms of mitigating the dominance of platform 1's market share. If this is not true, then the other 2 configurations might perform better on that regard. Meanwhile, consumer surplus is always the highest in the industry-wide configuration. So this confirms the trade-off we talked about just now in terms of this mitigating market share and consumer surplus improvement. So the sufficient condition here is this large enough advantage of platform 1 but that can be alternatively stated in terms of the equilibrium market share of platform 1 being larger than 1/2. So here we can talk about some additional questions such as what happens if we endogenize this formation of the configuration. So on that regard, we try to explore this a little bit and we impose some assumptions. So we assume that formation of the links requires mutual agreement, and we assume that fringe platforms make a joint decision in terms of the link formation. Then we show that if this platform 1's advantage is large enough, zero interoperability emerges. So this is quite a bad news because over here, this is saying that in terms of both objectives, either star or industry-wide is better. But this is saying that neither of them will arise in the equilibrium. So again, suggesting a divergence between the platform's optimal configuration or the equilibrium configuration and what is good for the other policy objectives. Okay, so let me briefly show the related literature here. So obviously this relates to the competition between platforms and the existing work on network interoperability, compatibility, and connectivity. Okay, so there are various works on this line focusing on quantity competition. We are more related to those looking at price competition. There are also recent works that look at asymmetric platform competition and interoperability. So a special shout out to this forthcoming management science paper by David and his co-authors on data sharing between generalists and specialist firms. Okay, so relative to all these existing works, I would say that our contribution is to propose a interoperability framework that analyzes this notion in 2 dimensions, strength and configuration. And in terms of methodology, we propose a network-based approach to model and analyze interoperability. So from here, we get 3 conceptual takeaways from this analysis. First, what are the implications of increasing interoperability strength? We show that there are 2 main effects. Okay, so platforms either internalize substitutions to the partners or internalize complementarity with partners. So we want to emphasize the existence of these 2 opposite effects, and we highlight them with the contrasting configuration of industry-wide and correlation, showing that the price implications can be quite different depending on which effect dominates. Second takeaway, we directly compare configuration. The main message here is industry-wide configuration does not always maximize consumer surplus in this symmetric setting due to the price effect. And we try to uncover a little bit more on what structural properties of this network configuration leads to this price effect. So we show that a more concentrated link allocation is the one that drives down the price effect, that drives down the price, because that corresponds to the sharpest insider-outsider distinction that gives rise to this complementarity logic. Finally, we compare configuration in this asymmetric dominant-fringe setting. We show that there's a potential trade-off between 2 policy objectives of mitigating market share dominance and increasing consumer surplus, where star performs better on this market share dominance regards, but perform worse than industry-wide configuration in terms of increasing consumer supplies. So that's all from me.
Thank you, Tat-How. So now we have a discussion by David Ronayne. In the meantime, if you have any questions, you can write them in the chat or simply raise your hand. David?
Yeah, hi, I'm just gonna share my screen. Can you see this?
Yep.
Can you see it? Okay, great.
Yep.
So yeah, thanks so much for prompting me to look at this paper. And I had the expectation that I would need to give this more time than an average discussion because I expected it to be high quality and difficult work. Nonetheless, I allowed myself enough time to look at this of an average discussion. And indeed, I was right. I shouldn't have done that. So I opened it and was immediately upset that Tat-How is up to his usual standards. So I apologize if that results in a substandard set of comments, but let's see. So thanks so much again. Network interoperability and platform competition. So first of all, lots of lovely things to say, but I think, you know, they're not just pleasantries. I think they mean something as well. So, you know, the focus is super interesting and relevant, and, you know, his bibliography gives you an idea of that it's interesting and relevant. There's a real surge of papers on this stuff now, but generally not with the technical depth and elegance of this paper. So I think this is a really good standout example. So it's more general than many applied theory papers on this topic, yet provides clear messages that can be stated in very intuitive terms, and the authors really do that very nicely. Maybe there's a slight issue in the sense that because there's actually the full intuition, you unpack it so well later in the paper. Actually, in the introduction, you try to do an overview, and it's kind of difficult to do an overview of what's going on. But when you unpack it later, it's really complete and clear. So I thank you for that, but it is a tough job to do it in the intro. So the result statements are really elegant and helpful in distilling, and he put up this a less pixelated version of this equation. This is a great example, right? So on the first expression of this thing, the thing not in the brackets, is the sort of standard IOE thing. You know, you can see in most differentiated price competition models, you're going to have an effect of n. It goes in the natural direction, and this H0 is about the density of the sort of marginal consumer for the firm, because it's the guy who's just sort of indifferent in terms of their product differentiation preferences between this and the next best one for themselves. You can think about that PDF, which represents the differentiation of preferences being more spread out or more tightly pushed together as how differentiated the products are. So it's all the natural stuff we know from many models there, multiplied very nicely by this expression, which is introduced by the authors, this thing in the brackets, which is all about their strength, interoperability configurations. And the walkthrough of that was very nice. And the fact you have such a nice parsimonious expression, and at the same time, these chains or paths, you were calling them in the talk, of logic related to the Jackson network theory stuff underneath that all is really a very appealing combination. You litter this with contribution markers along the way. In other words, tell us pinpoint exactly how this corresponds to known and how it differs to known and received papers. So the overall point of interoperability and configuration matters was made very elegantly and clearly. And for me, your methodology is perhaps more the main contribution. And that's what came across to me, rather than the sort of maybe theory I'm saying. Let me talk a bit more about that. So comments on your assumptions. You know, when I think about this topic, for me, the elephant in the room was this single homing restriction. You know, there are just a lot of markets in this space where multi-homing is rampant, or one of the key issues. And theoretically, multi-homing is, you know, this isn't just a sort of a why don't you do X? I mean, it does just interact with all the key forces, right? I mean, it interacts with interoperability, network effects, and competition. And I don't know how to handle this. I'm not saying you have to do it or something, but while I was reading it, I was sort of uneasy about this. And I feel like I didn't get an example that really made me get rid of that. So we think about messaging apps. There's a lot of current regulatory scrutiny on that. I think if you just think how many messaging apps you have on your phone, most people in the audience probably have more than one. Even in telephony, right? I mean, I have 3 SIM cards. And well, maybe we're more international than most, so maybe there's more single homing there, but nonetheless. The other thing that comes straight to my mind is you know, that I would like to know about eventually. I think probably not in this paper, but you know, these are just very general comments. Is I instantly am thinking about asymmetric oligopoly analysis when I think about these sorts of markets. And you indeed have a flavor of that motivation when you do your fringe and main competitor stuff. But of course, it's a non-strategic fringe, right? And it's great that you push in a direction that you can easily, I mean, none of your paper's easy, but you can do that, right? And that's great. But you know, that was another slight elephant in the room for me. The assumptions on interoperability parameters, and I think Jacques asked you a little bit about the second one. So you have a sort of two-way symmetry one that's much more natural, like IJ and JI is the same. And then you have this exchangeability, I'm calling it one, where you can essentially rename the firms and it doesn't do anything. So the firm labels are somewhat exchangeable. And the combination was somewhat restrictive. And I was thinking about it in terms of you writing down these different graphs, and I was thinking about degrees of freedom. So I think in your case, under the main assumptions in the symmetry and exchangeable case, when you have 3 players, you have only 1 degree of freedom given the parameters. And that's why all your examples are n equals 4 or above to give some richness. And there you have 6 links, but only 3 degrees of freedom, right? As in you specify freely 3 of the strength parameters, and then the other 3 are completely nailed down by that. So I found it helpful to think about sort of how restrictive this is. And it's not completely restrictive, right? But I thought a way to get to kind of quantify how restrictive it is was to think about degrees of freedom. And so I felt that it was quite restrictive. Nonetheless, I think you picked out the 2, these equal size coalition and the complete network, very natural. I think those are the 2 cases that, if you're going to be symmetric about things, come right to mind. I suppose my concern, I mean, what I was thinking about is, are these actually the only 2 plausible cases that your analysis really allows for under these assumptions? I mean, there are other things that I think satisfy the assumptions, like a ring, but I mean, I don't see that as terribly plausible, right? So are there other plausible ones as well? I mean, because in some sense, why not make your analysis and life a bit easier and just look at these cases one after the other? Now, I do see that that would get rid of a lot of the things I liked, like this beautiful chain logic and all these nice expressions. So I don't know, maybe I was thinking it could be easier and quicker for the reader to get to the meat, to do, you could consider, I'm going to do the complete network, then I'm going to do equal size coalitions. And in the appendix, we've got a unifying framework that covers these 2 and some other cases, just to get to the meat faster. But I suppose it depends if you're primarily looking at going to a theory or an applied crowd, maybe. Some cheaper comments. Binary interoperability seems to have some relevance. For example, in your disk system idea, I wonder if you might be able to go a bit further if you were to restrict the space of if you just look at the binary links. This disk system example made me start thinking about. I don't know if that simplification would help. Obviously, you're doing things continuously, so it would require something else. I felt to really get a data sharing world, and you mentioned this near the end of your presentation, we need some scope for uni or bilateral choices over the links rather than having them imposed. The same side and cross-site network benefits are assumed to be the same, but that's a very cheap point. Overall, I feel that this model is a great laydown and first kind of really putting down apparatus, right, rather than very specific assumptions to really look at a case. And so it's got this foundational flavor. But these are some assumptions when I approach this topic that I felt were left out by your contribution. And then I had this, I apologize, not thoroughly worked through, but it's sort of, just to discuss, and maybe you have an answer. I'm worried about tipping in these markets. So I was thinking about, I'll send you these slides. I was wondering about perturbing your equilibrium, slightly perturbing consumer behavior from your symmetric equilibrium. Do we spiral away from that into a land of asymmetry if we do that? Sort of standard equilibrium perturbation tests. I was wondering about the stability of it. And I kind of think it's interesting if the answer is yes or no. Because if it's no, well, that's a nice robustness point. But I worry in these markets with these feedback loops and so on that you get these natural asymmetric outcomes. And maybe that's why we see such asymmetric industry configurations. And I sort of sketch a potential exercise looking at stability on this slide. These last 2 slides are very quick, Alex. 3 working papers that you don't mention that I think you might, and I highlighted one in yellow, so they're all on interoperability. And the last one I really like because it talks about a couple of the, my big points on my assumption slide. So it's way simpler in other dimensions than you, okay? I think it's a duopoly. It's Mark Bourreau and others. And I saw them presented at Erie. I thought it was very nice. And I really like the way the tricks that they did to look at an oligopolistic asymmetric, I think duopoly. So I shouldn't say oligopoly. So that's worth having a look at. And yeah, I had a bunch of minor stuff, and that I'll just send you a scribbled PDF.